problem with the AXI is it kind of assumes this utility is observable. So in the AXI model, right, the utility function is like some function from infinite sequences of actions and observations going on. But this doesn't necessarily capture like all the sorts of agents that we want to be able to talk about, because you might also want to talk about agents that have preferences about things they don't directly observe. Right? Like, for example, suppose I want to have many friends, right? So what kind of preference, what kind of function is this? Like, I don't have like a counter in my field of vision saying, now you have 7 friends, right? Now you have 8 friends. And it's like something that I only can indirectly infer in some way. There's like some uncertainty involved. And yeah, this is like true for like many examples, even kind of the famous paperclip example. Right? You just want to build a paperclip maximizer. So the paperclip maximizer also wants to maximize how many paperclips there exist out there in the world. It's not like the number of paperclips that it sees on its camera, right? Because it can be anywhere. And it's also kind of related to so-called reward hacking, right? Because like if I want to maximize paperclips, then I should be caring about the actual paperclips and not just about something that is perceived the same way a paperclip is perceived. If I have a camera and someone sticks a picture of paperclips on my camera, then if I'm a paperclip maximizer, I'm not supposed to be happy with that. So yeah, so how do we even talk about it? How do we describe such a utility function? What is even the type signature of the utility function that we should have? So this was problem 3.
So what you wrote is like it's the entire sequence of action observation, which is it does capture a lot, right? Like if the clippy observes the paper being stuck to the camera, that could like bring down the entire utility function, and likewise, like, if you just see your friends every once in a while, that could still be like captured by this. But is this a setup for AIXI, or is it like just like momentary observations already have rewards?
So technically, for AIXI, momentary observations already have rewards.
Yeah, so that's a very narrow.
Yeah, but that's not really such a big difference. I mean, if you can sort of write this utility function in terms of some sum over time of something that only depends on the history so far, then you can always like like if I have here like a furious AXI that demands to receive rewards on every round, then I can add like a small adapter here, which kind of just records. So the observations are going here, like in the actions are going here, and here there's some adapter that just like records everything and computes the reward according to some hard-coded function, and then gives it here. So this entire box can be regarded as like sort of, less good. Yeah, sorry.
But that's still like going from your first star to person, like only like the reward only depends on the
Actions
up to
So
now.
I'm just saying the restriction that the rewards have to be like part of the observation is not really a big restriction.
Yeah, but I guess the
So what you said about the history contains information about like the picture being stuck on the camera. So that's true, but there's like some issues here. So you're saying something like, let you observable be defined as the expectation of like the true you conditional on some d in like a times so this would be like, so you're saying we can kind of do some kind of transformation like that and start with some unobservable rewards with the utility function, and then have a utility function which then kind of reduce everything to an observable utility. So this, I mean, yeah, you could do it, but there are like several problems with this. One problem is that so one problem here is that frequencies guarantees don't translate. So if you are converting to the optimal, like you observable for a particular environment, it's not the same thing as converging for the optimally true. So yeah, I don't know. Maybe in some contexts it's just fine to talk about regret bounds for the observable. In other contexts, it might be not fine. For example, like earlier we talked about motivations for frequencies guarantees. So, for example, if you're talking about like, why agents are selected, then it's not obvious at least that so this translation kind of loses something, and it's not obvious that this is like okay to lose this. Another thing is like how do you specify your utility function, right? So I mean here, well, first of all, this thing, it kind of assumes some probability space in which neutral is defined. What it even is the truth? Like what is even the type signature of the state? So we still need to do at the very least some work to explain this. And after we explain this, there might be like this transformation. It might also not preserve other things like computational complexity. Right, so if we have like some theory which only talks about observable utility functions and like characterizes sample complexity and characterizes like computational complexity, like for agents with particular types of utility functions, then this transformation here doesn't like preserve necessarily any of those things. Like it doesn't say like the assumptions, like the standard assumptions the theory has about the observable. It's to tell us what assumptions we need to have about the true. And it kind of seems like a relevant question. So, in the end, if you want to actually construct, like your own certain actual paper-plate maximizer, but it seems like, at least in the context of alignment, we want to be able to create AIs that do specific things. So, building like a paper-plate maximizer or building like a diamond maximizer seems kind of a necessary step towards building an align. Building an align seems like something that's kind of strictly more complicated than that. And even that is not clear how to do. If you don't know, if you don't know how to. But this is, just writing this equation is the best some kind of suggestion of some kind of an existence proof. That yeah, maybe there exists some utility function I could write that would kind of express maximizing diamonds. But how do I actually write this utility function, right? And yeah, this is one thing. And also again, going back to like actual alignment, if we imagine talking about something like if you want to be able to talk about things like one agent is aligned to another agent, right? So what does it mean that they are aligned? It means that they're kind of share the same utility function in some sense. But how can they share the same utility function if their utility function is not even in the same domain? Well, what does it even mean? So we need to engage with these questions to be able to talk about alignment at all.
Going to the frequentist thing you said earlier about this, it just seems to me impossible to ever do better than just maximizing this expectation, right? I mean, how could you ever do better?
I mean, in full generality, it's impossible, but in some cases, it is possible. So I have to post about imperceptible reinforcement learning with imperceptible reports, where I show there is some family of utility functions, which I call semi-instrumental utility functions, for which you can actually maximize. You can actually do have regret bounds, despite the fact that the utility function is not directly observed. And the reason, the way it works is because you can conduct some experiment that measures the utility function. Okay, so it's actually not necessary, in order to have a frequentist guarantee or a regret bound, it's not necessary to actually observe the utility function. It's only necessary that you can do some experiments in any given moment of time. There's some test you can run, which will tell you how much reward you had in the beginning of this test. Which is very different because this test, for example, might be costly, it might be destructive, so you cannot just continuously run this test in the end. It's actually different kind of learning problem.
Okay.
But I'm a little confused of why that's not captured by this form of utility function. Because in that case, you could include an action of I'm performing the experiment and then corresponding observation of what the outcome of the experiment was, and have this utility function.
I'm not saying that it's not captured by it. I mean, it's certainly captured by it in the sense that if you're just doing kind of Bayesian decision theory on this utility function, you will define, right? This is not the problem. The problem is that if we want to actually know what the regret bound is that's satisfied by the agent, then we need to talk about this thing. It's not enough to just talk about this. You kind of informally the regret bound without talking about this thing.
So if I understood, it's not only you don't just want to observe that the result of the experiment is a high utility, but even if you don't perform the experiment, you would be happy if you knew that it would provide a high utility or something. So it's not purely, the reward is not purely based on the result of the experiments or something.
It's like we want to have an algorithm that in any environment or in its hypothesis class will converge to the optimal possible expected utility in this environment, where you talk about this utility, but not this utility. This is just a strictly stronger condition. Like having a low regret bound under your truth is just a strictly stronger condition than having a regret bound under the opposite. Like there's like another term in the regret otherwise, which appears because of like kind of different environments that kind of look the same.
So or something like the instrumental utilities or rewards are like a subset of these for which we can have regret.
The instrumental rewards are a subset of possible like the truth for which we can have a regret. But like the general theory of what kind of regret bonds we can have for what kind of your truth is unsolved. This is like this is kind of related to partial monitoring. The enforcement version of partial monitoring. So there is like actual mathematical substance to the question which is not answered. You're saying. So problem 4 with AXI is what I call the privilege problem. So this is what I mentioned earlier, that in AXI, the description complexity is measured in an agent-centric way. Because like we're talking about the description complexity or like the length of some program which describes the environment, where like the environment is described in terms of in an agent-centric way. Right? You have like this notion of environment, which is like mapping from histories to distributions over observations, and like those things, we kind of describe them by some programs, and we say that the length of the program is a simplicity, but this is not how kind of Occam's razor is actually used in science, for example. When we talk about like in science, we talk about like the simplicity of some equations which describe the world not from an agent-centric perspective, but in terms of some degrees of freedom which are natural from just a pure physical point of view. Like, describing the world in terms of fields or particles or quantum fields or string or whatever, but definitely not in terms of like the pixels in my retina, right? If I kind of try to write the equations for how like the colors on my retina behave over time, according to quantum field theory, those equations would be very, very complicated. And this thing is, it has all sorts of weird consequences. Like you could kind of try to look at it from different angles. For example, there's something which, like one way I like to illustrate this problem is saying, imagine there's some robot going around, right? And then someone throws a towel on the camera, and the towel completely covers the camera, and now everything in the frame is zeros. So this event, everything appearing as zeros, has very low Kolmogorov complexity from an agent-centric point of view. Therefore, the agent can easily entertain hypotheses such as the first time someone throws a towel on my camera, I don't know, the side of gravity will reverse. Because why not? Like this hypothesis will not be much more complicated than the other hypothesis that this will not happen. So it would kind of be very, it would anticipate that there's like, a sizable probability of weird things to happen after every event of low complexity from an agent-centric point of view. Now, it's true like always true in learning theory and correct conceptually that when we encounter for the first time something which has some simple property that no other data point before had, then we should be expecting that maybe now some new behavior will begin. Like when we look at generalization properties, always kind of when you kind of cross a frontier of some low description complexity kind of surface or something that kind of separates the data space, then the generalization always kind of stumbles at this point because there's like multiple plausible continuations. Like, we've always seen the function of even numbers. We never know, we can never be sure how it behaves in odd numbers because maybe there's a term in the function that's only zero for odd numbers. So, but again, here it's important what measure of complexity we're using. We're using agent-centric measure of complexity. Then the agent fails to generalize across events that are special from an agent-centric perspective, which is very weird behavior if like you're thinking in terms of like the world-centric or some bird's-eye-centric observation. And it also has various symptoms like if you know about the article that Paul Cristiano wrote that the universal prior is malign. So in that article, it kind of shows that agents informally, that agents that can behave according to the universal prior, but it really works for any simplistic prior which is agent-centric. That such agents would very easily come to believe that they are living in some kind of a simulation and end up conducting some kind of a causal trade with the simulators. And this effectively allows the hypothetical simulators, which are not really simulators, to kind of convince the AI to do whatever they want. So this is kind of very weird and science fiction phenomenon, but it's actually, I think, not that weird in science fiction. I mean, it's science fiction, but there's a real basis there. Like when your agents are when your epistemics are agent-centric, then you naturally converge to things which are kind of simulation hypothesis shaped and end up with some really weird beliefs from the perspective of someone who doesn't share the same reference points for their epistemics. Yeah, actually, in the post, I also talked about problem 5, which is which was the lack of descriptive theory. Yeah, I kind of forgot about that. So maybe I'll say a few words about that too. So the descriptive theory thing is that, like, the AI side is in some sense a very prescriptive perspective. It tells you, if you want to have an agent, then this is what you should do. Right? This is like you need to maximize expected utility of the solving part, and that's like your agent. But when we want to take a descriptive perspective, like we just have, we have some systems in the world, and we want to ask, is this system an agent? If it's an agent, like we want to ask questions like, is particular system X an agent? Or if it is an agent, then like for example, what is the utility function of X? can also ask what is the prior of X. Like in AXI, the prior is always the sum of the prior, but even the sum of the prior is not unique, right? Because there's different universal Turing machines that can choose different class of prior. Or maybe some other properties of agents. And it seems that such a descriptive theory is necessary because, like, because like, otherwise it's not clear how this kind of idealist theory connects to kind of non-ideal, like, approximate objects we have in the world. And when they're kind of just doing formal reasoning about agents, they like to say things about, if we design a system like that, then maybe agent will arise in it, which will do something. Like, what does it mean that an agent will arise there? Or like, so this type of reasoning kind of assumes some kind of descriptive theory. You can even say that some given thing is an agent or isn't an agent. So it's not enough to just give one like canonical reference example and say this is an agent. And even more kind of practically, if we want to do alignment, then one of the ways we can try to do it is by saying, okay, humans are agents with a certain, like, what does it mean? How do we formalize the notion of something being, of the system being aligned? Say that, okay, humans are agents, they have some utility function, we want to be aligned to that. But what does it mean that humans are agents and they have a utility function? What do we mean by that? There's a lot of like philosophical complexity that kind of hunts that. And so this calls for some kind of a descriptive theory, which, even ignoring all the other problems 1 to 4, AXI doesn't really give us, unless we were, So like, unless we are in a universe where all the agents are just literally copies of AXI, and this is like the only type of object we care about, then our theory cannot be, it is not complete.